Hello, ladies and gentlemen. Our group experiment is called Bang Goes the Balloon, and I am St. Jin Bang, and in my group there are also Jiang Kim and Milano John. We chose to choose the experiment that will let us enjoy the fact that we're experimenting. So we chose something related to water balloons. The question that they asked us to answer was how the balloon moves and in what condition it pops in. So we all know that there are just sometimes that water balloons don't pop, and we tried to find out whether it's because of the strength we throw it at, or the amount of water inside the balloon, or the surface of the wall we throw it at. So in our experiment, we made water balloons of different weights, and we threw it at the wall with different strength, and the wall had different surface texture. So we hypothesized that it will pop the best when it has the most liquid inside the balloon, and when we throw it at the most strength as possible with the roughest surface, it will pop the best. So we thought this because if the surface is rougher, there will be more friction applied when it contacts the wall, making it wear off. And if we throw it at more force, then it's going to explode more. And if we put more liquid, according to Newton's second law of motion, the more weight equals more force. So we thought that the more force will make it explode better. We first thought that it was due to the scientific term elasticity that the balloon pops, but which can be explained like this. If the substance returns only partially or not at all to its original state, it is considered inelastic. If too much force is applied, the material is in danger of reaching its elastic limit, and therefore can't go back to its original state. Once the elastic limit is passed, the material will experience permanent reshaping, also known as plastic deformation, and will no longer act as an elastic substance. You can easily see this by hanging a weight from a spring. If the weight is within the spring's capacity, the spring will bounce back. However, if the weight is too heavy for the spring, the weight will pull the spring straight, therefore making it inelastic. But later, we found out that impulse was also key to why water balloons pop. And impulse can be shown like this. Impulse has been, we can calculate impulse by the momentum at the start and the end. So this formula shows that the momentum at the end subtracted by the momentum at the start equals the impulse. But because we have already made our experiment and we couldn't change it because it's too late, we just stuck with the elasticity idea. And now Jiang will tell us about what happened in that experiment.
Thanks, Jun. So now I'm going to explain what equipment we use. We only use water balloons, obvious for our experiment. We use water to fill the water balloons, the surfaces, which are rough and a smooth surface. We also use the tap and hoses to fill up the water balloons. Our procedure was simple. Firstly, we filled up the water balloons while trying to vary their weight. Secondly, we divided the water balloons into 3 weight categories. We threw the water balloons with different amount of forces applied, and finally, we reported our test results. So this is what we got from our experiment. So when we threw a water balloon at a rough surface, all the balloons popped except for the one small balloon thrown at a weak force that didn't pop. And surprisingly, when we threw at a smooth surface, results were quite heavily changed. When we threw at full force, one of the water balloons, as shown here, one of the small balloons didn't pop. When we threw at a medium force, a medium balloon didn't pop, and a small balloon. And surprisingly, when we threw at a weak force, only one full balloon was popped, and 2 medium balloons were popped, and none of the small balloons were popped. And now I will hand over to Lynn, who will talk about our variables in our experiment, our conclusion, and what we can improve next time when we do this experiment again.
Thanks, Gian. As for all experiments, there are variables in ours as well. Some of these included like the force of the throw, which would change quite easily, the elasticity of the balloon, and which is what in the end contributes to what if the balloon pops, and the precise amount of water in our balloon, which we tried to measure and keep roughly the same, but we could have done so more accurately. We could improve these to minimize the effect they have on our experiment for next time, and we've come up with a couple of ways. For the force of the throw, we could design a balloon launcher which would propel the balloon at a consistent force for the same amount for the whole time, which we would be able to adjust. To make the elasticity of the balloon similar, we could use exactly identical balloons, which we tried to do but were slightly different. We'd have to test them all first. For adjusting the water in the balloon, we had to measure everything out infinitesimally accurately, which we haven't been able to do due to the time constraint. Our conclusion was we found out that our hypothesis, which was it was more likely to pop under these conditions, were actually correct. Since there was more if there was a rough surface, it would create more friction, which would wear down the balloon more. If there's more water, there would be more weight, which would increase the force of the throw. If there's more force, the balloon would compress more, which would make it reach the elastic breaking point, or the elastic limit, which would go to make the balloon deform, or as we like to call it, explode. And the people that we need to thank.
Oh, right. Okay, so we have our bibliography here, and this is actually all the research that we did. And we have to give thanks to my friends Jamin and Frank and Andy, who helped us make the water balloons, and Mr. Kamek for giving us the idea of impulse, Alex for giving us the idea and telling us about elasticity, and Stephanie and Kira who taught us how to make the water balloons.